All right, this is for aerospace engineering. It is activity 3.2.2, orbital mechanics, which is a project lead the way PowerPoint presentation, introducing you to Systems Toolkit and how to use it. I had already done part of this PowerPoint, and I see I need to make one more adjustment that I forgot to take care of. Drats. Standing by to make a correction. All right, so I know I had already shown this PowerPoint presentation and gotten started with it with my aerospace students, but for the benefit of my physics students, here, have a look at this exciting PowerPoint slide. So this is using STK from a company called Analytical Graphics Incorporated, AGI. And I would love you students to learn how to use it a bit. So a reminder, an orbit is a closed path and it goes around and around. Natural objects in the universe tend to be in elliptical orbits, sometimes parabolic orbits, occasionally, very rarely in hyperbolic orbits, and basically never in a circular orbit. It just never happens. An ellipse is a conic section, the intersection of a plane with a cone, where the plane is tilted at an angle to the cone axis. Yep, nice. So a circle is a special case of an ellipse where it's kind of the two focal points are coincident in the center of the circle. So a circle is a locus of points, constant radius from one fixed center. An ellipse is the locus of points that is the sum of the distance from two focal points. Great. And satellites orbiting the Earth, well, the Earth would be at one of those two focal points. Mathematically, the major axis is labeled by 2a. Algebraically, a is no longer acceleration here, it's just the long axis of an ellipse. B is the minor axis of the ellipse, 2b actually. 2a is the major axis. Then there's also the distance c, defined as the distance from the center of the ellipse to one focal point, which we're not going to care too much about. These are examples of highly useful orbits, and I could play the video, so sure. The little dots represent the location of satellites in these various orbits. Each orbit serves a highly useful purpose, whether it's military or civilian. We're tilting our axis a little bit. I could talk on and on and on about each of these orbits, but I already did that last week. So right now I'm just going to finish playing this video once and then move on. Here's another video. Great. So with STK, which is what's being used to create these animations, you can have extreme control over visually what is presented. So here's the central body is planet Earth. And even on the night side of it, we can make out, oh, here comes Africa, and it's heading towards sunrise as the Earth rotates. And the colors and the line thicknesses and the labels and the information that's displayed, all of that can be controlled by the user using STK. So it's an extremely useful analysis tool if you want to design a mission that serves some purpose. Their training scenarios can guide you on practicing doing different scenarios. Maybe you want to protect the southern border of the United States from drug smugglers. Maybe you want to have a satellite that detects fires breaking out somewhere in the wilderness of California. Maybe you want some way of assessing damage from an earthquake. And here, this is just pointing out that the global satellite position system that we developed is being expanded so it not only deals with objects near the surface of the Earth, but it even reaches out to geosynchronous orbit now, which is an upgrade from the original system. So everything you're seeing here is being created with STK, and Molniya is the name of a Soviet orbit. It's very useful for communications with high latitudes around the Earth. Geosynchronous is highly useful for communication around Earth's equator. So they really serve two different regions of the planet. And then there's other ones like Sirius XM has their own preferred orbits that they use, which is logical for that company. They have 3 satellites, and at any one time, if one of them is transmitting line of sight to you, then you can listen to your favorite radio station if you subscribe to their service. And there's also low Earth orbit, geosynchronous orbit. And in case you didn't notice it, geosynchronous means the satellite is orbiting the Earth at the very same amount of time that it takes the Earth to rotate once, which is a sidereal day, 23 hours, 56 minutes, 4.091 seconds. And that's slowly becoming longer. And this just shows that we have a communication system that replaces our old ground systems with 3 geosynchronous orbiting satellites, and that allows communication with deep space probes continuously in view. All right, so much for that slide. Johannes Kepler worked out the 6 parameters for describing an orbit. 2 deal with the size and shape, and then there's the orientation, and finally 1 that deals with where the satellite is at that moment in time in the orbit. So here we go. Yikes. A formula for calculating eccentricity. I don't believe we're going to be using this formula, but you might want to jot it down. Eccentricity is the square root of 1 minus b squared over a squared. B is the semi-minor axis, and A is the semi-major axis. All right, moving on. This orbit is one that we could start off doing on STK. So I'd kind of like you to practice using STK and practice your math skills at the same time. So here's what I'm going to tell you. As I look at this slide, I'm holding up my protractor against my computer screen. Yeah, laugh all you like. And I'm measuring that I'll work in metric, that the diameter of the Earth on this computer screen is, let's say, approximately 4.8 centimeters. Okay, so jot that down somewhere on a scratch piece of paper. Diameter 4.8 centimeters. The diameter of the orbit in this screen is something like 6.0 centimeters. So first of all, an exercise in scaling. If the radius of the Earth is 6,378 kilometers, you'll need a calculator. What is the orbit radius shown in this diagram? Okay, so how do you do that? You should do a ratio, right? We're going to say that the diameter of the Earth is 2 times 6378. So the diameter of the Earth is 12,756 kilometers. You know, I don't think we really want to work with diameter. We want to work with radius all the time, anyways. So let's go the other way. If the diameter of the Earth on my computer screen is 4.8 centimeters, then the radius of the Earth on my computer screen is half of that, 2.4 centimeters. And the radius of the yellowish orbit would be half of its diameter. So half of 6 centimeters is 3 centimeters. Now we have a simple ratio we can set up that says the radius of the real Earth, 6,378 kilometers, is to the radius on my computer screen of 2.4 centimeters as the orbital radius of that satellite shown in STK is to 3 centimeters. So calculate, please, what is the estimated orbital radius of the satellite shown on this slide? Okay. That's strange. Two strange answers. Well, okay. And that's what I got as well. So I'm going to go with 7,970-ish. We could just round that a bit more. Let's just call it 7,800 kilometers. Great. Now I'd like you to actually do that in STK. So launch STK. Create a scenario. We could call this orbital mechanics. You're not allowed to have spaces in the title. So what they do is they smoosh the words together, sometimes with underscores, and capitalize each major word. And this is, if I were to describe it, I would say this is Project Lead the Way, activity 3.2.2, orbital mechanics PowerPoint. So what I would say, one day isn't going to be quite enough for this. So I'm going to set my stop time to 2 days from now. I would say that's plenty of time for what we're doing. It's launching, takes it a while. Oh, thank you for that message. I will close this out and try to go fix my mistake. Yeah, thank you. I set it to 117 days instead of the 17th day of March. Okay, so 17 March. Let's try that. Thank you, student, for catching my mistake. All right. The 2D map is sometimes useful, so I won't give up on it. The 3D visualization option is beautiful, so I tend to use that. I guess we can go tile vertically. Yeah, that's fine. Okay, so I'm going to insert, by the way, that view that was shown in the PowerPoint was looking down above the North Pole of the Earth. So I'm going to change my orientation to look down from above the North Pole of the Earth. And now I'm going to choose to insert a new satellite. And I would just use the Orbit Wizard in this case, insert. So I'm going to make the color try to match the slide. Seems like about that color. I am going to have it equatorial, so inclination 0 degrees. As for the altitude, I have to do a quick calculation. So if it's at 7,800 kilometers elevation, orbit radius, if I subtract 6378 from that, I have an altitude of 1,400 kilometers. Well, more like 1,420 kilometers. Pretty close. And I'm going to hit OK and close. So you're saying, hey, that looks a lot like the PowerPoint slide. There's a couple things. I can shut off the display of the title, but if you zoom out far enough, it shuts off. Now there's a way you can edit that so that it always stays on. And that is if you go to Satellite and you go down to the 3D graphics and you go to Model. Down here for detail thresholds, at what distance does it show everything? And right now the answer is only when you get within 600,000 kilometers of it. The marker with a label only shows up when you're within 1.4 kilometers of the satellite. So the point is, if you move these sliders, you can adjust the distance at which the satellite orbit is visible. I'm going to cancel that and try to think intelligently. What is it I'm trying to do? So I would like the simple model. No, I guess not. A point visible, and you can go out across the solar system. Let's try applying that, seeing how it goes. So now, no matter how far I zoom out, that point still shows up. But I see that this line isn't, well, let's go back to that PowerPoint. Oh man, that seems to be a reasonably close match, right? This color, that line, that dot, compared with here in STK. I guess there's one minor difference. They have a little open circle for the satellite point. In STK, if I really care about it, I can go and choose the 2D graphics attribute to be a marker that is just like an open circle. That didn't work. Okay, how about we pause for 3 minutes? So in STK, because it's not just a PowerPoint slide, we can run this animation, and now you can see the satellite orbiting the Earth spinning below us. You can see that the Earth spins counterclockwise as you look down on it from above the North Pole. You can see that the satellite is going around the Earth in less time than it takes the Earth to rotate once. And we can edit the thickness of the line, we can make it a dashed line, we can make it labeled appropriately, and so forth. So anyways, there's the first slide. I'm now going to put us back. Well, let me stop the animation, reset it. Now back to our exciting PowerPoint presentation. There, Now, when you look at that slide, you should say, hey, I can do that. Now, they're showing the slide as it appeared on January 1st, the year 2000 at 7:14 and 30 seconds in the morning. I don't really care. I mean, if you really want, we could create a scenario that matches their dates. We don't care. Here's a new exercise for us. Oh my goodness. So they have a video that we can play. Let's see what theirs looks like. It's showing these four different satellites orbiting the Earth, and the way the Earth is oriented, these would be polar orbits. So instead of just staying above the equator all the time, they lined them up not quite at north to south. I can see the way the Earth is tilted. So these are just highly inclined. We're just going to make it exactly vertical. And here's what we're going to try to do is actually build this scenario in STK. So if I go back to how the slide first appeared, I already did the measurements ahead of time to save time a little bit. I'm going to tell you that the semi-major axis, so take a look, it's color coded. The red circular orbit is eccentricity 0. So I ratioed that radius to the radius of the globe of the Earth on the slide, and I get a semi-major axis of 51,000 kilometers. So we're going to attempt to build this slide. First one, so we're going to create 4 satellites. The first satellite will be the red one. It's going to have an orbit radius of 51,000 kilometers, and we're going to make it kind of vertical. So in STK, I'm going to shut off this first satellite. We don't even really need it anymore. Boop, now it's not being displayed. I'm going to choose to insert a new satellite. I'll use well, I would just, yeah, sure. Let's use the Orbit Wizard for starting. It's starting off with a nice red color. That's good because I want this to be that deep reddish color. It's going to be a circular satellite. I'll call this thing E0 for eccentricity, or even spell it out, right? Yeah, no, just E0. E for eccentricity. I'm going to incline it 90 degrees so that it's a polar orbit. And instead of the altitude, oh gosh, I can once again subtract the radius of the Earth. So if I go 51,000 minus 6378, the altitude is going to be approximately 44,620. Apply. Okay. I'm going to close it for now and just zoom out and reorient my globe and zoom out some more and play this thing and say, yes, the satellite is going counterclockwise around the Earth the way I would like it to do. Okay, yikes. And if you're not too careful, tilting this thing makes it go crazy, right? So be careful. Let me zoom back in. Is the Earth right side up? Yes, it is. Okay, and like that. Okay. On the PowerPoint slide, this red orbit, to me it looks a little thicker, so I'm going to choose to make the line a little thicker. I'm going to go to 3D graphics, no, 2D graphics attributes, and I'm going to make the line width a bit thicker. Apply. And then I could just glance at the tab without closing it and say, well, yeah, that looks better. So I'm going to close out the properties window. What's next? On the PowerPoint slide, the next one is this sort of yellow with eccentricity of 0.4. So in STK, what I can choose to do is duplicate. I can copy my satellite. Let's see, how do I do that? I right click, I copy, and then I right click. Well, I guess not. I right click, I paste. So now I have a second satellite that looks identical to the first one. I'm going to call this eccentricity 040. Oh, actually, it's the second one I want to edit, isn't it? So eccentricity 40, meaning 0.4. Crazy. All right. Now for this second satellite, I clearly need to make some changes. So I'm going to double click on it, bring up its properties, and for orbit, I'm going to change the eccentricity value to 0.40. In addition, I need to make it a distinctive color. So under 2D graphics, I need to make it that sort of darkish yellowish color. Apply, OK. Well, it's building it to the left when I really want to build it up. So how will I do that? Hmm. I'm going to change the argument of perigee to 90 degrees and see what that does. Okay, well, it's going down. So if I make this an argument of perigee of 270 degrees, then it should look like it's going up. Okay, so that was argument of perigee under the basic orbit parameters for the yellow orbit. Ta-da! And now when I look at it, oh, look, there's the constellation Orion. Can you see it? Here's the three stars that is Orion's belt. Here's his sword. This would be the star Rigel. There's the star Betelgeuse. Nice. All right, well, so Orion's in the background. Cute. The Earth is now hanging at the end of Orion's sword. And when I play this, we can see, I can speed it up a little bit. We can see the satellites orbiting the Earth. One thing that's a little bit off is they're not starting at the same place at the same time. So if I go back to the first satellite and I change its argument of perigee to 270 degrees, I believe that means they're going to be both starting at the same point. Yeah, as they go around the Earth. Okay, on the PowerPoint. Huh. The next one is this sort of purplish colored eccentricity of 0.60. So in STK, I'm going to take what I successfully did and I'm going to copy the second satellite and now paste the second satellite and rename it as E60. I'm going to change only two things. First, the eccentricity becomes 0.6. And secondly, under 2D graphics attributes, change the color to that kind of purplish color, if that's it. Looks close enough to me. My wife would say, "Oh no, Mr. Turek or Phil." She would say, "Try this color." Yeah, maybe so. Okay, so now when I play this scenario, you can see the three satellites with different eccentricities orbiting the Earth. But wait, the PowerPoint had four satellites. This last one is a green one. Can you create it yourself? It has an eccentricity of 0.74. It's kind of a light green. Oops, wrong one. Oh, drats. Forgot to tell you something else too that would have helped. Kind of late. Ta-da! Oh, the markers don't really show up very well, do they? The locations of the satellites in their orbits. You can barely see them here. So I'm going to pick one. I'll start with E0. And I'm going to try to upgrade the model so that the marker drats. Marker. So on the 3D thing, I'm choosing a dot, but I can choose the pixel size. So if I change it from 8 to 16 pixels for the orbit marker, apply that, see what that looks like. There. It's showing up much better with 16 pixels. Notice how it disappears when I zoom out? Okay, so I can fix that by choosing to have the marker visible at a greater distance from the Earth. Like here's 10 million kilometers. Now I can zoom way out, but actually it's got the label as well, and I don't really want the label shown, I want just the marker. So let's try leaving the point large. There. Now, no matter how far I zoom out, I have 16 pixels showing me where that satellite is. So I'm going to do that for all of these satellites. So that was E0, E40. I go to 3D graphics model. Marker is a point. Pixel size is 16 instead of 8. Apply. Okay. Do the same thing for the next guy. Also, make sure that the point is visible at a great distance. I forgot about that. Let's go fix that for this guy. Model. Point visible at a great distance. The rest, we don't care. And the last one, 3D graphics model, pixel size for the marker 16, point, maximum viewing distance all the way to the right. Everything else above that down to 0 is fine. And reset my animation, zoom out a little bit, and play. With the Earth in Orion. The point educationally is to note that all of these 4 orbits, oh, and we reached the end of the animation time. We set it to only 2 days. We've just gone through our 2 days. So, yeah, they disappear when it's outside their time range. Back to the educational point. These 4 orbits each have the same average distance from the Earth. They have different eccentricities. The red one is circular. The green one is the most elliptical. And yet, what you can see is that they all take exactly the same amount of time to orbit the Earth once. So, period of time doesn't depend on eccentricity, does it? Okay, back to this exciting PowerPoint slide. You have theoretically built this slide yourself. And now you can understand a little bit of details like, oh, that pixel size of 16 was maybe a little bit too big. This looks more like pixel size 12. You can make the line thickness different. You can make the colors different. You can play with it. Oh man, here's the next slide. What if you have different sizes for the orbit? For this one, I measured it for you and decided that the eccentricity for each of these 2 orbits is the same value of about 0.68. And what's different are their semi-major axes. So I'm going to pose the question to a random student. Student with initials TG. Shall we build this slide, yes or no, in STK? Okay, the answer is yes, so let's go build this in STK. These were fun. I guess we can leave them in our scenario but when I uncheck these boxes, it shuts them off from view. And really, in STK, you should always be saving your work all the time. I've not even saved it once. Nice. And again, I just love the fact that I can recognize that's Orion right there. The 3 stars of his belt, his sword, and there's the Earth. We can make the Earth, you know, you can't zoom in on the stars, but you can zoom in on the planet that's in front of the stars. So just for fun. All right, so we're going to build this new slide. Again, the parameters from this slide are, they both have an eccentricity of 0.68. They have different semi-major axes. I'll give you the values in a moment. And actually, I'll tell you already. So for one of them, it's at 44,000 kilometers. And for the other one, it's around 55,000 kilometers. So in STK, we would choose to insert a new satellite. And there's another way you can do this, but I'm going to define the properties this time, not bother with the orbit wizard. Insert. So we really should be using a two-body propagator for now so that you don't see how the orbits get distorted by the true shape of the Earth. In this slide, it looks like that was it was a polar orbit again. So we'll make the inclination 90 degrees again. It's for the semi-major axis for this first one. Let's make it 44,000 kilometers. Eccentricity of 0.68. I guess we can make the argument of perigee 270 again. And we need to change the color. So under 2D graphics attributes, make it that sort of darkish greenish color. And by the way, if you don't like the palette, you click on other and it brings up all these choices, of course, in spectral space. I think that green line was something like about like that. Like before, okay, I'm going to leave the line as being thin. I'm going to go to the 3D graphics model. I will set it so that it has a pixel of about 12 this time, so we can actually see it. And set the point to be a great distance and the other little details to be close. When I apply it, I can bring it up on the 3D graphics window. This whole thing is huge. So I'm going to close this out, close that out, zoom out a bit. There's the first one. For the second one, so that is satellite 6. If I right click on satellite 6 in the object browser and I choose copy, and then right click on satellite 6 and choose paste, it duplicates it. And I'm going to I guess it called it satellite 1 when it duplicated it. It's got its own crazy naming style. The only value I need to change is the semi-major axis. Instead of 44,000 kilometers, make it 55,000 kilometers. Apply. I'm going to demaximize this window so that you can kind of see things as you make the changes. And there it is. So, okay. Here is the Project Lead the Way slide, but I've added the markers so you can actually see where the satellite is in its orbit. And that was it. I can slow the animation down with the time step decrease. And now the whole thing takes a little bit longer because they're moving a little bit slower. You should start to notice they take different amounts of time to orbit the Earth. When they're far away from the Earth, they slow down. They're basically fighting to go uphill from Earth's gravity. When they are close to the Earth, they are speeding up as they head towards the Earth. They're heading downhill. They pick up speed. All right, so there's that slide. There's no animation for this. This was just a slide. The point is, you can build what you see in these slides using your STK skills. Of course, there's physics here. The semi-major axis is the distance from the center of the ellipse to the farthest point away from the center of the ellipse. It is the average size of the orbit. Boop. The 2 points terminology that we care about is apoapsis, which is the farthest point from the central body. Periapsis is the closest point to the central body. When the central body happens to be the Earth, then we change the ending to G for Earth, G, Earth. So apogee, farthest point from the Earth. Perigee, closest point to the Earth. If it were the sun, we would call it apohelion and perihelion. If it were the moon, apolune and perilune. So some planets have names for them, and the generic name is just apoapsis. We can talk about the altitude as well. So apogee altitude is measured to the surface of the Earth instead of to the center of the Earth. G means Earth. Here's the generic name, apoapsis, periapsis. For its circular orbit, those two altitudes are the same value. It's a perfect circle, right? It says here perfectly circular orbits cannot be achieved in real life, right? Mathematically, we can pretend that the Earth is a point mass. That's called the two-body propagator. And for satellites orbiting the Earth, we don't really talk about their semi-major axes. We usually talk about their orbital period or their orbital altitude. This looks scary, but this is Newton's version of Kepler's third law with one tweak. So they use the Greek letter mu to represent the product of capital G times the mass of the central body. That's their only tweak. Otherwise, you might recognize this as t squared equals 4 pi squared r cubed over gm. So they took the square root of both sides already. There you go. You've been using this equation already. The square of the period of the planet is proportional to the cube of its distance. Let's have a race. And here's the animation. Let's duplicate this. Of course, the period ends in 1 minute. So I'm going to leave this as your homework assignment. How about that? Can you scale the Earth to the orbits, build these satellites in STK, these colors, line thicknesses, this orientation, let's just make them equatorial. So let's shift it so that the North Pole is in the middle of the Earth. So we're looking down from the North Pole. That means your inclination would be 0 degrees. These are all circular orbits, and the period just ended. So how about that as an exciting homework assignment?